In this video now, we're going to consider another first-order differential equation. However, it is a vector-valued first-order differential equation where x is a vector and A is a matrix. And so inspired by the solution that we got in the scalar case in the previous video, we're going to try a solution that looks like this, so that the solution x of t looks like the exponential of some lambda rate, and then multiplied by a vector v, and v is the same size. It has n elements in it, just like the state x. And so if we plug this into this differential equation, x dot, the time derivative of this solution that we're going to guess, just brings the lambda down in front. And so the derivative x dot is given by this quantity. And then we write a times the state again. And the state is e to the lambda t times v. And since this equation actually has to hold for all values of time, this allows us to cancel the exponentials out of both sides of this equation, which leaves us with this very familiar equation, which is the eigenvalue-eigenvector equation. And just to remind you again, the value of this eigenvalue and eigenvector relationship is the fact that the lambda and v are the special scalar. So the lambda is a scalar, just a number, and the vector, the v is a vector. They're these special number and vectors such that when I multiply the matrix A by this vector, I actually get the same vector back, simply scaled by this quantity lambda. And that's a very interesting relationship, and v and lambda are properties of the matrix A. And so we find the eigenvalues and eigenvectors from the matrix A. And so notice that you'll also remember that we don't just have one eigenvalue and eigenvector. In general, for an n by n matrix, we will have n eigenvalues and n eigenvectors. So that's the easy case. There are some complicating factors, so that's what this caveat down here is saying. The tricky cases here are where there are cases where you have n eigenvalues, but there are less than n eigenvectors. And so this changes the solution just a little bit, but in general, this gives you a good idea about the solution. And it'll be the focus of this, this class for primarily. So the state x of t then can be written as any of the eigenvalue-eigenvector pairs. So in this case, I have lambda 1 paired with its eigenvector v1. And so this by itself, this term by itself, is a solution. And the same can be said for the second eigenvalue-eigenvector pair, as well as any eigenvalue-eigenvector pair. And if one of them is a solution, because of the linearity of the original differential equation, any combination of these is actually going to be a solution as well. And you can test this. So you can instead take this entire expression, substitute that into the original differential equation over here, and just like we've done here, but now do this with many terms, and you'll find that we get the same equation, except there will be many copies of this for each eigenvalue-eigenvector pair. And so we can compactly write that as this sum. These Ci or the C1, C2, and so on, these are just simply scalars that can involve more or less of each of these different terms into the solution. Now I'm going to present an alternative way of thinking about the solution for this linear system of equations. So if you remember, the expansion for e to the x, where x is just a scalar, is given by this formula. So what's neat is that we can define a matrix exponential, which is the exponential of a matrix, where m now is a matrix, an n by n matrix. And so we define that essentially in the exact same way. So 1 is replaced by the identity matrix, and then every time you see an x, you just replace it by the matrix M. And so similarly, we get the same expression, but now these are now matrix products to compose, for example, like here, m to the third power. And so if we define the matrix exponential in this fashion, then e to the at, where a is a matrix and t is the scalar representing time, then just replace m by at, and you get this expression here. And if that's e to the at, we can actually take the derivative of that with respect to time. And if we do that, the identity element does not have any dependence on time, so it becomes 0. AT is linear in t, so you just get the matrix A. And then in the quadratic term here, the 2 cancels the 1/2, and you're left with a squared t, and so on. And so essentially you reduce a power of t. If we forget this 0 element and factor out a factor of a out front, then what's left, because this is an infinite sequence, what's left is an expression for e to the at again. And so the derivative of e to the at is simply ae to the at. So if we let this be x, if e to the at is x, then the derivative of x, x dot, is equal to a times x, which is our differential equation we were trying to solve. And so this is another way to represent the solution. So now we have 2 different ways of representing the solution, and now I'm going to connect these for you. So this first line is simply just reminding you what the scalar solution for that differential equation is. And so now that we have the vector valued first order differential equation, our solution, vector valued solution, goes like this. And that's what we said on the second slide. To connect this with what we had on the very first slide, we observe what happens to e to the at when we multiply by an eigenvector of A. So V is an eigenvector of A. When we write out the expansion for the exponential, and we factor this V inside, we multiply it through, then we get a term that goes with V, and then we get a term that goes, this lambda V comes from this term where we had A multiplied by V. And we use the fact that AV is equal to lambda V, the eigenvalue-eigenvector relationship, in order to produce this lambda. And so if we have A squared, this means that we're going to get lambda squared here. And so if we pull, you notice that we're able to pull out a factor of V that's in common across all of these elements. And what's left is this scalar exponential of lambda t. And so by multiplying e to the at, which is a matrix, multiplied by the eigenvector of A, we produce one of the, what we're going to actually call modes, or one of these solutions that come from the eigenvalue-eigenvector pair. And so another way of thinking about this is that up here in this solution, we are writing a matrix e to the at multiplying by the initial condition vector x of 0. One way of connecting this is to see that x of 0 can be expressed as a combination of the eigenvectors of A. This is a nice feature because if we have n eigenvectors of A, they end up, we can say that they're actually linearly independent, and that forms a basis that allows us to represent any other vector in that space. So x of 0 can be expressed in terms of these other all of the other eigenvectors of A. And if we do that and plug this equation into this equation, that provides us, and then use the fact that this that we get this type of solution of a single mode with each of these V terms, then we recover the solution that we had on the first slide. And so by doing this expression of the initial condition and understanding how the eigenvector pulls out a particular mode out of e to the at, this allows us to connect the two solutions that we have. And so this is a nice, both are a good way to represent the solution, and they give a different interpretation of the behavior. Going forward, we're going to be talking about each of these terms as representing a mode because the speed of the response is given by this lambda. So the different lambdas, the values of these different lambdas, will actually characterize the way that the solution behaves.